good afternoon, or good evening, depending on where in the world you are watching this event. Welcome to the next installment of the Sommelier Series brought to you by Nagarro. Just for background, Nagarro is a global product engineering company, digital product engineering company with a team of over 13,000 people spread across 27 countries. Nagarro solves complex business challenges through agility and innovation. Nagarro's Sommelier Series pairs speakers from different backgrounds and expertise to create a strong, ideally perfect exchange. My name is Suresh Sunderrajan. I'm the Associate Laboratory Director for the Energy and Global Security Directorate at Argonne National Laboratory, which is based in Lamont, Illinois. This is about 25 miles southwest of Chicago. I'm here today with Dr. Venkat Srinivasan, who is the Director of the Argonne Center for Collaborative Energy Storage Science. And we're here to talk about the future of energy storage. I'd like to take a couple of minutes, if you don't mind, just to set some context before turning it over to Venkat for him to to provide an introduction as well. So Argonne is one of 17 Department of Energy national laboratories. We trace our roots, if you will, to the work by physicist Enrico Fermi in the 1930s and 1940s. You may remember that he participated as part of the Manhattan Project, and his claim to fame, clearly a Nobel Prize winner, but really was in demonstrating the world's first self-sustaining nuclear reaction. This was actually work that was done when he was a professor at the University of Chicago. And the first reactor was built actually in a squash court under the football stadium, under Stagg Field at the University of Chicago. Once that successful demonstration happened, it was decided that the experiments were probably a little too dangerous to be conducted that close to a major city. So they moved to what was then a remote site in Palos Hills. And the forest in that area was called Argonne. And therefore, after the Second World War, Argonne was actually created as a national laboratory on July 1st of 1946. It was the first national laboratory, and it was created with this mission of developing nuclear technology for peaceful uses of nuclear energy. Today, Argonne has an annual budget of about $1.2 billion as of fiscal year 21, with about 3,500 full-time staff. Roughly half of these staff are engineers and scientists engaged in research and development, while the remainder are in various support capacities to execute this research. A majority of our researchers have advanced degrees. We're a mission-driven organization. The DOE mission, the United States Department of Energy mission, is to ensure the US prosperity and security by addressing energy, environmental, and nuclear challenges through transformative science and technology. And as such, we work across a broad range of domains, leveraging cutting-edge scientific and computing tools to execute multidisciplinary, team-based science. Now, one such domain is energy storage, with a specific focus at Argonne on batteries. Today, Argonne has one of the largest, if not the largest, dedicated team of scientists and engineers working on battery research across the world. And as just one proof point, in the last 5 years, Argonne staff have published almost 1,000 peer-reviewed, highly cited articles in electrochemical energy storage and conversion. These account for roughly 5% of all the publications in this domain in the United States. With that context, I'd now like to turn it over to Venkat, who, as I mentioned, is the director of the Argonne Center for Collaborative Energy Storage Science. And as such, he coordinates Argonne's energy storage strategy and execution. Venkat, please, if you could introduce yourselves and also please, could you talk a little bit also in the context of the global clean energy transition and specifically the role of energy storage in affecting this transition, please.
Suresh, thank you so much. First of all, I wanted to make sure I thank the organizers. This sounds like a fantastic session. Had a chance to look at some of the earlier presentations and talks that came out from the Sommelier Series. Very interesting, and I'm looking forward to this conversation. Suresh mentioned I'm at Argonne National Lab, the largest energy storage lab in the country, or maybe even in the world. And I've been an energy storage person pretty much all my adult life. I think starting in 1995, I started working on batteries, worked on many different battery systems over many years, looked at everything from sort of looking at batteries for space applications. This is batteries that are used in the Hubble Space Telescope, electric vehicle batteries, grid storage batteries. And I will say that it's been extremely exciting watching the kinds of things that have been going on in the last, especially the last decade. I remember 20 years ago saying something like, it's the best time to be in batteries. And I think I'm finally correct about it. It's really the best time to be in batteries is today. It's a really fun ride. I think it's an exciting area for those of you interested in getting into sort of solving the problems with energy storage. Many people ask me why I got into storage. And I want to sort of quickly say that I've been hearing from my friends and family members about how their batteries are really bad and I've got to do something to fix it. My 9-year-old son complains about his iPad running out of charge all the time and how it takes forever to charge. My 80-year-old parents tell me that their iPad runs out of batteries all the time and it takes them forever to charge. So I've been jokingly telling people, I just want to make sure that my family is happy. That's why I work on batteries. But there is a bigger reason that I work on batteries. It's because I think it's becoming very clear that batteries and storage writ large is an enabling technology if we have to solve the climate crisis. And I want to take a few seconds to just talk about why this is such a critical challenge, right? I mean, I think it's becoming very clear that this decade is going to be the crucial decade for us to do something about climate change. We've known about climate change for, I don't know, right, 40 years or so. When I got into the sort of the whole battery field in earnest 20 years ago, all I could hear was about the big issues related to climate change. But I feel like during those days, it wasn't real. These were these graphs that we were seeing of CO2 emissions and projections in the future, what implications that had on climate change, what did that mean for maybe the melting of the polar ice caps. It didn't feel like it was something that we were experiencing. I think that has changed in the last 5 to 10 years, right? For those of you watching all these hurricanes that seem to linger and flood our cities, the fires that we're seeing all over the world, the fact that the permafrost is sort of melting in the Arctic, all of these are real things that are happening. It's happening right now, and it's all accelerating. And all of a sudden now, I think everybody all over the world is recognizing that we have to do something about this challenge. I mean, I've been arguing it is the single biggest threat to humanity. That is until COVID showed up, and now we have a bigger threat to humanity, which we have to solve. But certainly, I think long-term, we have to find a way to sort of get out of this climate crisis. And really what that means is, first, we have to stop burning fossil fuels. It is the single most important thing we should be focusing on. I will say that you can't flip a switch and stop burning fossil fuels tomorrow. There's going to be a momentum. It's going to take us a couple of decades to transition our economy away from fossil fuels. And I know people have been talking a lot about pulling carbon from the atmosphere. Carbon capture is becoming important. I think also the reality is that we may not be able to reverse where we are with climate change. So what this means is that we have to start thinking very, very hard about how are we going to start to adapt to this reality. But having said that, right, we have to move away from fossil fuels if we have to have a long-term sustainable path towards climate change issues, right? And that's really where I think energy storage comes in. Let me just give you some context for this. 25% of all the carbon emissions comes from electricity generation and heat production. We have to move away from fossil fuels, coal and natural gas for these sources, move to solar and wind. Solar prices have actually gotten to be cheaper than coal in many parts of the world. Wind is also following in terms of lower cost. The challenge is the sun doesn't shine all the time, the wind doesn't blow all the time. So what do? We have to store the energy. That's where energy storage, batteries start to come in and play a crucial role. So that's the first important part. How do we generate electricity? The second part is, can we start using electricity as a primary energy to move things around, right? How do we move towards electric cars as opposed to gasoline cars? How are we going to ensure that as we go to the future, trucks, planes, ships, all of these are powered by electrons as opposed to being powered by some sort of a fossil fuel? Again, this is where batteries come in. We've already seen Teslas on the road. That's exciting and interesting. This is obviously a trend that I think we have to take advantage of, but there's a lot more to do there if we have to get to a place where we don't emit carbon from our transportation sector. But storage is going to be across the board, right? Think about industries, which accounts for another 20% of the carbon emissions, or buildings and homes where we again burn a lot of fossil fuel. Moving to electricity for all of that is going to require better storage technologies. So to some extent, right, the one technology that plays an absolutely outsized role when it comes to solving our climate change issues and securing our future is some sort of a storage device. Specifically, I'm super excited about batteries, but there are many other storage devices we should be thinking about. If you can find that 1 or 5 or 10 different chemistries and mechanical ways of storing energy, I think we'd be in a much better place. And that's really the reason why I work on these technologies, because I think it can have a huge impact. Suresh?
Thank you, Venkat. That was extremely helpful in setting context for the discussion over the next 40 or 45 minutes. Let me take just a second in case you're joining this meeting late. I'm Suresh Sunderrajan. We have with us today Venkat Srinivasan. Venkat leads the energy storage program as the director of the Argonne Center for Collaborative Energy Storage Solutions here at Argonne National Laboratory. And we're here talking about the future of energy storage. Venkat, with that context, if I could take just a half a step back, batteries are clearly ubiquitous, and you talked about the challenges all of us face with our cell phones and our laptops. You talked about electric vehicles, and you talked about applications in the grid. Can you help frame, if you will, these applications for us? I mean, are these just bigger and bigger and bigger batteries, or is there something different that is required in terms of the applications and the technologies? Please.
That's a great question, right? And let's start with the one that all of us have been struggling with, our cell phones and our laptops. Before this meeting started, the organizers made sure that the two of us had our batteries charged up in our laptops, right? That's the first thing we all think about. So, if you think about a cell phone, right, you want it to last all day, hopefully last more than a day. Same is true for every other consumer electronic device. And the second thing you probably want it to be is you want it to charge really, really fast, right? So that's the most important metric. You have to have, last a long time, you want it to charge fast. And what that means is that you have to have very high energy density. Energy density equates to sort of the runtime of your cell phone or your laptop. So that's a very important metric. And the second one is you want it to have high power during charging. And if you do that, then you could shove the energy into the battery fairly quickly. You can charge it fast. I know everybody wants a 5-minute charging battery. That's the metric that you want. Oftentimes, when you're talking about a cell phone, many of us change our cell phones every 2 years. So number of cycles or number of years the battery lasts is not that important. These are small devices. You might be paying $1,000 in the United States for a brand new phone. The battery probably costs like $5. If it costs $7, you're not going to worry about it too much. You won't even know that it costs more money, right? So things like cost is not that important for that application. It really comes down to energy density and charge time. Those are the two most important metrics. Now, when you move and start getting to a transportation system, so let's say you want to buy an electric car, the first thing that strikes you is what's the range of this electric car? I mean, especially in the United States, right? People drive 300, 400 miles in their gasoline cars, and they want an equivalent in their electric cars. What that means is you need a high energy density battery, very similar to what we were talking about for these consumer electronic applications. That's great. Now, nobody wants to sort of wait around for half an hour, 45 minutes charging these batteries up. For those of you who live in Chicago, it's been below freezing for the last 4 or 5 days. I do not want to be standing outside trying to pump in electrons into my vehicle for the next 30, 40 minutes if I'm stuck on the road somewhere. So I think long term, people want to have fast charging equivalent of what we can do with gasoline. So give or take 5 to 10 minutes. That's the big challenge. So those two are the common metrics that exist between consumer electronic batteries and electric vehicle batteries. But there are other things that are extremely important for electric vehicle batteries. One is that you've got to make these batteries last 8, 10, 12 years, because nobody wants to change the battery every X number of years, maybe 3 or 4. That's very important. You're going to be charging the battery quite a bit, maybe 1,000 times through the life of the vehicle. That's going to be extremely important. You cannot afford to have any sort of safety issues. You probably can't have that in a cell phone either, but imagine the catastrophic nature of a car fire. You've all seen those pictures. You have to build in safety at every level when it comes to electric cars. And there are other metrics that I won't talk about, but certainly high temperature operation if you're living in a hot climate, low temperature operation if you're living in a cold climate, all of that becomes important. So what happens now is that, consumer electronics, couple of metrics, electric cars, the metrics start to open up. The third one that I'll talk about very briefly is stationary storage, storing electricity off of solar and wind that we were talking about before. There, the battery is not moving anywhere. So you don't need energy density. This battery can be huge. It can weigh a ton because you're not going to move it anywhere. Unlike your cell phone or a laptop or your electric car, where the battery itself is moving with the device, here it's not moving. So you don't have to worry about energy density at all. But you have to worry a lot about how long the battery lasts. For example, a solar panel, in a home might typically last 25 years. You want the battery to last 25 years if you can. Not 2 years like a cell phone, not 8 or 10 years like an electric car, but more like a couple of decades. Imagine if your battery lasts 100 years like we would have with pumped storage, like in Niagara Falls, right? That would be fantastic if you can do that. The second one is cost, right? Electricity is a commodity. And if all of a sudden we're saying that we're going to move to solar, and now I got to put a battery because the solar is intermittent, the sum of the solar and the battery and the cost of electricity better be very similar to what we're paying today. So in Illinois, where Suresh and I live today, we probably pay 8 cents a kilowatt hour. I used to live in California. There I was paying more like 24 cents a kilowatt hour. So depending on where you are, the battery may have to get cheaper and cheaper as electricity cost gets cheaper, because you got to have parity. Otherwise, nobody wants to pay more money in order to get to a cleaner source, right? So in the end of the day, right, the metrics for a grid storage are probably the most sophisticated because we're trying to do something, incredibly different. The last thing I'll say about grid storage is right, the metrics of how the battery ought to operate depends upon what you're using the battery for. So you could imagine that there are cases where you might be using the battery only for a few seconds. So this is for firming of sort of electricity, which might be going off frequency. You might be using it for 3 or 4 hours, say when the clouds kind of go over the sun in the afternoon and you want to use the battery during that time. Or you might be using a diurnal, right? Store batteries, energy all through the day using solar and a battery, use it all night, power your home. Or you might be looking at all week when you don't have the sun, say in winter, or the wind doesn't blow. Or you might be thinking seasonal. So the time scale of storage in a stationary can go all the way from milliseconds to many months. And depending upon which application you choose, you can actually see different metrics between cost and energy density and things of that nature, where you may have to sort of play with all these different metrics. So again, different applications require different metrics for it to be successful. And as you go from consumer electronics, which is the easiest, you go to electric cars, which is a bit harder, and grid storage, where it gets really hard because of the cost constraints and the cycle life constraints, the calendar life constraints for that application. Hopefully that kind of provides some context there.
That's super helpful, Venkat. I think you're clearly sharing some of the challenges in the number of different attributes that have to be considered as you look across different applications: energy density, charging time, lifetimes, charging cycles, safety paramount across all applications, the robustness to the environment that you might see, and of course, cost. Another question, if I could, just building on this, all of these elements are important, but we also, when we've been talking about batteries for the most part, but energy storage is broader than just batteries. We could have chemical storage. Certainly hydropower is the largest at the grid scale. Could you talk a little bit about how people should be thinking about energy storage, batteries and beyond?
Yeah, I mean, you bring up a very important point, right? I mean, there is a little bit of sort of the narrowing down to sort of talk about a battery, because a battery can do all sorts of wonderful things. But the reality is we have to keep our eyes open, and it's not going to be one size fits all. We have to have a multitude of solutions, right? You mentioned hydro, extremely important. Every country has some sort of a dam somewhere, but you're using that to produce electricity using a turbine where the water is flowing. Lasts decades, hundreds of years, right? You can go a century with repairs on these things. Once you pay down the cost of building the dam, after that, the cost of electricity is extremely cheap, and it's storage like no other, right? It's extremely reliable, really fantastic, right? That's kind of the one that we all think about. There are other forms of storage that you can imagine. One great one is thermal storage, right? Imagine ice and water, right? So you freeze it during times when electricity is very cheap and you make ice. And then when the electricity prices go up, let's say in the afternoon in a hot climate, you might cool the building down using the sort of the stored cooling of the ice that you have and melt it down, right? So another easy application, turns out that's actually real. There have been companies that have looked at ice storage. Extremely cheap, extremely easy to use, and also works really well. What it comes down to is asking yourself, what's the application you want to go after for that particular thing? There you're going from electricity in to heat out, right? That's kind of what you're trying to do there. You can think about hydrogen, which is a great chemical storage media. We've been talking about the hydrogen economy for many years. I think there was a time when we thought we could be moving in passenger cars using hydrogen. I think the reality is that we've come to realize that maybe a battery is a better way to do that. But hydrogen is going to play a crucial role as you think about it in terms of chemical storage, whether it's going to be in sort of the very, very long duration aspects where you're trying to store energy for weeks or maybe multiple weeks or months, where hydrogen can play a crucial role. There are some challenges there because how do you store the hydrogen becomes a crucial issue. If you have a salt cavern, people have been trying to pump the hydrogen down in those areas. That's one way of doing it. But you have to have the salt cavern close by for you to be able to do that. In all of these, right, there is a challenge of what is called dispatchability. Are you stuck with the storage being in a particular location? For example, if it's hydro, then you're stuck because you have to have a river and a dam to kind of do that. You might be thinking about something like a pumped hydro where you may have to have a hill where you have to sort of move the water up and kind of bring it down, or you may have a salt cavern where you're stuck finding a cavern where you can start to use the hydrogen. The beauty of something like a battery is that it's dispatchable. I could put it anywhere. I can put it in my backyard. I can put it behind a building somewhere, or I can put it in a wind farm somewhere in the middle of nowhere, right? So that's the beauty of sort of a battery. So that's why there's a lot of focus on trying to see if we can find that perfect battery. But having said that, when I kind of look broadly at the energy challenge, I think we have to take advantage of every form of storage that we can get a hold of. If you can do thermal, do thermal. If you can do hydrogen somewhere, do hydrogen there. And if you can get pumped hydro, do that too. But if you can't find any of those because you're location problematic, or you have a space constraint, or you might be at a spot where you have no way to sort of access some of these other technologies, then a battery will also play a crucial role. But I do think that we have to sort of think about this in all the sort of the different contexts. The last thing I'll say is, I had friends who sort of taught me the importance of demand response. So, the easiest thing to do when the electricity price goes up is to dim your lights just a little bit. And if everybody dims their light, the electricity demand goes down pretty significantly. It's the cheapest thing we can do. There is nothing to do. All you have to do is dim your lights, right? So demand response, I think, is going to play a more and more of a crucial role. And I think we have to have a holistic way of thinking about this, right? It's going to be, all of them working in concert with some sort of a smart system that sort of controls all of them so that the consumer doesn't have to see it. And maybe that's the way we have to evolve in the future.
Thank you, Venkat. That you brought in a very important concept there, dispatchability. And I think the other concept, that electricity is truly a commodity. Maybe it's a branding question for some of the marketing geniuses in our audience here to say, how can I get a premium for renewable electrons versus, other sources of electrons, shall I say? But pushing a little bit in the, sorry, go ahead.
We should be talking to Elon Musk. I think he's shown us the path to, at least in the vehicle market, as to how one might be wanting to do that. So
that's right. That's right. But pulling on that cost thread for a second, there's some very interesting dynamics. And I remember reading recently that, some article that talked about, it was a loose comparison. Loose is perhaps the operative word between Moore's law and kind of the cost decreases that we have seen with some battery architecture, specifically lithium ion. Can you talk a little bit about the trends that you're seeing and where do we go 5 years from now, 10 years from now? Will we continue to see this, dramatic? Yeah, I think I remember reading, orders of magnitude decreases 97% over 3 decades or something like that. Can we expect another 97% in the next 10 years?
Yeah, I mean, it's a remarkable question, right? I mean, I remember 10, 12 years ago, these batteries were super expensive to the point where it just felt like you had to buy a $100,000 vehicle for it to sort of pencil. I mean, never pencils out. A $100,000 vehicle is the only one that could be powered as an electric vehicle. And grid storage felt like just this distant dream. In the last 10 years, the cost of batteries have come down by an order of magnitude, right? That's just the reality. This used to be more than $1,000 a kilowatt hour. Today, we're talking about batteries that are approaching $100 a kilowatt hour. And, these numbers are a little bit murky, depends on how you define it. So, I won't get into that, but certainly a significant decrease in cost. And the main reason why the cost has come down is because of mass manufacturing. Very similar to what happened with solar. You might have heard about these gigafactories, right, that have been popping up. First, Tesla made the announcement they're going to build this 35 gigawatt hour a year factory. A typical factory used to be less than a gigawatt hour. Approximately a gigawatt hour is considered to be a big factory 10 years ago. Today, everybody is talking about 20, 30, 40 gigawatt hours a year as the manufacturing capacity to go after. And what that has done is that that kind of scale is something that people didn't think was possible. But if you can build it, and people have built it, the cost of these batteries are going to be significantly lower, because what you're doing is you're beating down the manufacturing cost. Today, the cost of manufacturing of batteries is, total cost of a battery is approximately 80% material cost, 20% manufacturing cost. And 10 years ago, it was more like 60% manufacturing, 40% materials, or something like that, right? A remarkable change. But that statement also tells you where we're going to sort of limit out, right? I mean, you're probably not going to see a whole lot more reduction in manufacturing costs, because we're already down at 20% of the total cost. And now we're going to be significantly limited by materials, right? So the thinking is that batteries are also about new materials. It turns out that material discovery is integral to finding better batteries. And there is an active worldwide community trying to find the next magic material. So the feeling is that as we start to get those materials to the market, we're going to start seeing the chemistry changes impact that floor, right? That 80% material cost is going to start to come down, because now we're able to find cheaper materials, or materials that are giving us higher energy density, things of that nature. So we are going to see, I think, maybe a reduction of a factor of 2 cost reduction sometime in the next decade. I think that's the expectation. The cost might come down sooner at a smaller scale, but really getting mass manufacturing is a real challenge in energy storage. It's a decadal challenge when it comes to sort of manufacturing of these kinds of systems. So it might be a decade before we see the cost come down by a factor of 2, but I think that's where we're going to be. Turns out for some of these grid applications, we may have to cut the cost further by maybe a factor of 4 beyond that factor of 2 that we're talking about. Things like that are going to be extremely challenging and extremely hard. It requires a lot more R&D for us to get there. But I think what we're seeing now is manufacturing has done its role, and now it's the job of new materials that has to come in and start to reduce the cost of these systems.
Thank you, Venkat. Sorry, it took me a second to unmute myself here, but no, that's really interesting. And I have a couple of threads that I'd like to pull on. But before I do that, just a quick note to the audience. If you have questions, we're going to go for another 15, 20 minutes between Venkat and me here in this conversation. But if you have questions that you'd like to ask Venkat, please put them in the chat, and we'll try to get to as many questions as we can in the time that we have allotted. So please feel free to add your questions as well. Coming back, Venkat, I want to pull on 2 threads. Both were quite exciting, interesting, I thought. One is this, you talked about new materials, and so I'm interested to hear from you, what new materials might be being explored. What is the potential? What is the time frame, and so forth? But there's a related question, and that was also something that you said. I think one of the many things that COVID-19 has, changes that it has created in all of us is an acute awareness of supply chain. I think it is much more of much more in the common vernacular now of supply chain issues than it ever was. And clearly, as you talk about these materials challenges, lithium and cobalt and nickel, some of these materials are hard to source. So could you talk a little bit about both new materials as well as supply chain issues, please?
Yeah, this is a crucial question, Suresh. I'm glad you brought it up, right? I mean, supply chain issues are front and center. Sustainability has become front and center. You sort of mentioned a couple of metals, right? So when you think about supply chain, right, the most important thing I think is having security. You have to know that you're able to get that material so that you can sort of guarantee that you can make the device so that you can sell it to the consumer. That's the most crucial thing. And so what has happened is that we're expecting the worldwide market for storage to take off. The numbers that I've been sort of estimating would be at a factor of 20 to 30 in the next decade. We have to increase storage capacity manufacturing by a factor of 20 to 30 in the next decade for the electric vehicle revolution, the grid storage revolution, all the rest of the stuff, right? That's kind of the where we are. That's exciting, right? It feels like, this means that there's a huge market, there's a market demand, people are buying electric cars, they're talking about grid storage. That's fantastic. But the question comes down to, do you have access to the supply? And so what that means is that we have to first ramp up the supply of all the upstream, meaning that the materials that have to go into these things, the mining that has to happen, the components that you have to make, all of that has to get up to that factor of 20, 30 in the next decade, and probably has to happen sooner. The second thing is making sure that we have a diverse set of places where the materials are coming from. If COVID has taught us something, it's that if you're dependent on one region, and if something gets disrupted in that region, then we are in trouble. So there are a couple of elements: cobalt, which is 50% of it comes from the Democratic Republic of Congo; graphite, which is also used in a battery quite a bit, which is 80% of it comes from China, where there's concentration of the elements in one region, where a small disruption can have a huge global impact in terms of this technology, right? So it's very important for us to think about supply chain of the materials we use today and combine that with the fact that we need better storage materials for the future. Right, so let's talk about that for a second, right? So today's batteries, as you were mentioning, has nickel, cobalt, manganese. This is on one side of the battery. A battery has three components to it: an anode, a cathode, and electrolytes that go in between. There are other components that I won't talk about. The cathode has cobalt, nickel, lithium. The anode has graphite. And that's the chemistry that's approximately $100 a kilowatt hour, gives you a 250, 300 mile range in your car, and the rest of the stuff that we're used to. So as we look to the future, we are trying to move away from graphite in our anode, and there's a movement towards silicon as the anode, silicon that's used in solar cells, and with some variants can be used in a battery, and actually gives you 30% more energy, cut the cost down by approximately 30%. It can fast charge, sort of has some interesting aspects to it. So there's a reason why the whole community is pursuing it, and I'm really hopeful that silicon will play a crucial role as we go to the future. That's on the anode side. On the cathode side, there's a huge effort trying to eliminate or minimize the amount of cobalt in the battery, but also minimize and maybe eliminate nickel in the battery. And that's because nickel prices have also started going up because of supply chain constraints, right? So that's a huge part of the challenge that we're pushing, while simultaneously we want to keep increasing energy density, because increasing energy density is going to be crucial for us to get more driving range, decrease the cost, and do all other things we need to do to decarbonize the economy. So those are the two big changes that are going on. These are what I would call more near-term changes. Another change that's going on is the transition from these liquid electrolytes that we use today. So all batteries today have a liquid electrolyte. That liquid is kind of flammable. That's the reason why batteries go up in flames. There is a movement to remove the liquid and put a solid into the battery, make it a solid state device. If you can make a solid state device, safety should go up, at least in the way we're thinking about it right now. But it also enables us to go to new materials. There is a particular material on the anode, lithium metal. Lithium metal is a holy grail for all of the batteries. For those of you who are using watches, before the Apple watches started coming out, those watches oftentimes had a lithium battery in it, or the cameras, when we all had cameras with flashes on them, that flash had a battery that had a lithium battery in it, except those were all primary batteries. You couldn't recharge it. And that's because if you recharge those batteries, they had various issues with them where they would actually go up in flames. We can solve the problem by putting a solid electrolyte instead of a liquid electrolyte. It turns out that's a huge revolution that has happened in the last 8 to 10 years. So as we look into the next decade, I think we want to slowly start transitioning to these solid state devices. And if we do that, it's going to give us a huge impact in terms of what we can do in terms of energy density. It's going to open up the doors for a whole lot of new materials for the cathodes in the batteries. It's going to start to provide, I think, the kind of changes that we're expecting in the battery world and can last us next 20, 30 years of innovation. So you can start to imagine better cell phones, but also better cars and better grid storage devices. There are other batteries other than the kind of lithium batteries that people also sort of think about. One of them that comes to mind is a flow battery. A flow battery is a lot like your internal combustion engine. So in a typical battery, right, you have a box and all the things are inside that box. And all you do is you go plug the box into your cell phone, or you might be putting it into your lawnmower, so your lawnmower, and just kind of using that. That's kind of how it works. A flow battery is a bit like the internal combustion engine in the sense that you have a tank where you store the fuel, and then you'll pump the fuel into a cell where you will react it, put out electricity, and then you'll store the product in another tank. So that's going one way, gives you discharging the battery so that you can get energy, and then you can charge it back up by flowing it from that other tank to the cell, kind of converting the chemical and putting it back into that first tank, right? So think of it very similar to your gasoline engine. If you make the tank bigger, you can go longer range. If you can make the cell bigger, it's like going from a 4-cylinder to a 6-cylinder, so you can change the power in your device. So that's an interesting concept that actually makes a lot of sense for grid storage. Turns out that we think flow batteries can be cheaper than lithium battery when it comes to long duration storage. And there we really have no dependence on cobalt and lithium and nickel. It's a whole other set of supply chain of materials that comes in. And there we can diversify and try to find new sources, right? So it's not one battery that's going to satisfy all applications, or as we were talking about, or even one storage technology that's going to satisfy all applications. So thinking as I look into the future, right, I think the importance of diversification is also because we don't want to be stuck with a supply chain dependence where we are, if one component is sort of bottlenecked, then we have a huge challenge in decarbonization. Essentially, what we have to do is find diverse chemistries so that we can go after different things for different applications.
That's very informative, Venkat. If I could pull on that sustainability thread that you talked about, some of what I'm hearing is certainly from what you said is diversify the material set, diversify the architectures, diversify the kind of depending on the application, what energy storage technologies you might use. One commonly used process to improve sustainability is recycling. Is that important in batteries? Do you see that being important going forward?
Absolutely. I remember 15 years ago, I used to live in, close to Berkeley, California. And Berkeley is a bit of a green place. So, I remember being at a sort of an open house kind of a situation where I was talking to the general public. And when I used to tell them I work on batteries, the first question they would ask is, are these things recyclable? I'm kind of confused about what to do with my battery. Every one of us probably has a couple of cell phones sitting somewhere in our drawer because we have no idea what to do with them, right? There is a lot of cobalt sitting in those batteries, by the way, guys. There's a lot of money to be made if you kind of find a way to kind of get it back to a source where you can get the cobalt. So I think there are two things that are important, right? As we were talking about before, any change in these kinds of technologies is decades in the making, right? Nothing changes overnight. And that's because chemistry is hard. Manufacturing of chemistry related devices are extremely hard. Everything is a decade out. So for the next decade, we are going to be using batteries that have cobalt, nickel, lithium, graphite, all these stuff in it. That's the first thing. So, and frankly, even after that, we probably need a little bit of cobalt and nickel, all the rest of the stuff, right? It's probably not going to be at a stage where we eliminate these things. Again, the idea here is to diversify. We want to have multiple ways in which we want to solve our problems. So more and more, in order to sustain this sort of this trend of having cobalt and nickel, and let's take the United States as an example, the US in the ground does not have enough nickel and cobalt. We just don't. So we can either import it, or we can find a way to get all those batteries in your drawers to a point where we can recycle, right? So recycling is going to play an extremely important role in ensuring sustainability, just for the supply chain perspective. But there's a second thing, right? These batteries have some pretty nasty components in them, right? I mean, you could be making, there's fluoride-based stuff in it. I mean, the electrolytes are sort of highly flammable. It's the kind of stuff that you don't want to be throwing somewhere in a landfill or burning somewhere and just letting it out to the atmosphere. You want a completely sustainable, as in a circular economy in the end of the day. And I think just for the purposes of where we are in the world and where we want to be 20, 30 years from today, circularity is going to be playing a crucial role. So I think both from a supply perspective, but also from just being circular, I do think recycling is going to be extremely important. I mean, I've been telling my people that have been asking me who are early in their career, they'll ask me something like, oh, what's most important here to work on? And I'll be like, oh, you should work on recycling, because that can have an incredibly important role in terms of how we can make this technology into something that we're all proud of and something that does not go into the ground. So yeah, that's a great point.
Thanks, Venkat. That's hugely helpful. You talk about circularity, and that reminds me. Certainly this innovation ecosystem is very rich. You've got innovations happening at universities, at national labs, at industry, and this is going on around the world. Can you talk a little bit about how things are progressing? Are you seeing companies lean forward into not just sustaining the shall I say, the performance, but also considering the cost and considering the sustainability and how they might be working with each other and the other stakeholders in the ecosystem?
Yeah, I mean, Suresh, you know this extremely well, right? The first step for any technology is there has to be a market demand. And I think, I remember back to the early 2000s where there was a bit of a clean tech boom going on. I used to live in the Bay Area at the time, San Francisco Bay Area, Silicon Valley was very close by. And there were all this money being thrown at clean energy, but therefore also into batteries. And this is by the end of the decade, we had a stimulus package in the United States. There was a global recession because the housing market crashed. And because of that, the governments were pumping in money, and the money started going into sort of energy storage technologies, right? The problem was the market wasn't there yet. It seemed to be at the cusp of taking off, but it hadn't taken off. So what we saw was a lot of interesting stuff that were coming out, both from the universities, but also from industry, because those are the ones getting funding. But it didn't translate into something that became real because it was not sustainable because the market wasn't there. Boy, has that changed, right? I mean, kind of, literally, I remember, when I was in California, first I saw one electric car, maybe two electric cars, and all of a sudden 2 years go by and every other car seems to be an electric car. I moved to Illinois. In the beginning, same thing, right? Maybe there's an electric car every once in a while, but now it's like every other car seems to be an electric car. This has taken off, and it's happening all over the world, right? Europe, it's certainly happening. I'm from India, and you're from India, and people are talking about it in India now. It's happening everywhere. It's become clear that either because of climate change issues or because this technology is new and exciting, and people want the next big exciting thing. There are reasons to go electric, right? So there are, this is becoming huge. So the market is there. What this means is that companies are going to be able to sort of compete and start to do things with it. Turns out that, as we were talking about, we just don't have a magic battery today that's going to satisfy all applications, which means there's going to be an incredible fight in the marketplace to try to capture and see if your technology is going to be the one that makes it. And my belief is that multiple technologies will make it, and there is room for many different technologies. What this means is that companies are starting to look very closely at academia and asking, hey, can I start to pull the next greatest thing that's coming out of a national lab and see if I can commercialize that intellectual property? So we're seeing more and more collaborations that are starting to nucleate between the academic and the national lab side of things, the R&D side of things, and the industry side of things. This, I think, is extremely crucial. One of the big things that, Suresh, you know this very, very well, right? One of the big reasons why it takes a decade to sort of manufacture is because if you throw technologies over the fence from our side to something that looks like the industrial side, it collapses because there are all these nuances in chemistry that have not translated itself, and we haven't taught them how this works. So there has to be this very close sort of collaborative way of doing things that's going to be extremely important. In the United States, this is becoming front and center. Recently, Argonne actually announced the creation of a public-private alliance called LibBridge. The idea behind LibBridge is that we want to create a sustainable long-term supply chain in the United States for lithium batteries. And the way we do that is by pulling together the public sector and the private sector, putting them all in a room and having those holistic conversations to try to figure out where is it that we want to be. How do we get there? Who are all the players that have to get us there? How do we create the workforce that's going to help us ultimately reach that sort of a stage? Because if we don't have the workforce, this is all for naught. So I think these conversations are happening, and this is happening in Europe. They have a large public-private consortium they've created maybe 4 years ago. It's happening, I think in Japan, this has been going on for quite some time, where they've been talking about how do you get the academic side and the industrial side together. I think those are going to be extremely important. The word ecosystem is a great word because it takes a village to get these technologies to market and do it at the pace we need to do it to solve the climate crisis. And the only way to do that is get everybody talking the same message, talking to each other, and ensuring that we're lining up towards the challenge and kind of marching together towards where we need to get to.
It's very inspiring, Venkat. Thank you. Maybe I could ask one quick question, and I see some questions coming in from the audience as well. So I'll switch to that with this last one that I'd like to ask you. I believe there's a number of students that might be listening in on this conversation. You've talked about a fascinating field, great market demand, incredible projections, very rich in terms of opportunities and challenges. If I'm a student and intrigued by this domain, are there things that you might recommend that they should focus on?
Yeah, I mean, there are many, many ways to get involved in storage and writ large in climate. I think climate challenges, right? I mean, obviously, if you are in a field like mine, so, people who want to be on the technology side of things, or, you can be a chemical engineer, a chemist, a mechanical engineer, a material scientist, all of these front and center, right? These are the kinds of people that the world is looking for. You don't have to be a PhD, you can be a master's, you can be a bachelor's. People are looking for all of those, and you can immediately play a role because these are, at the end of the day, chemical mechanical systems, sort of, in some cases the chemomechanics is intertwined, in some cases it's disparate, but really you can get involved in any of those technology fields. Turns out you can go even broader than that, right? I mean, it turns out that crypto is starting to become important for us, not in terms of currencies, but in terms of sort of blockchains, and using blockchains as a way to sort of protect and start to look at transactions, especially on the grid. So if you're in that area, that's fantastic too. I talk to journalists all the time, because part of what we have to do is communicate what we're trying to do from a scientific community to the broader audience, right? It's important to kind of get the word out, and part of getting the word out, and I learned this very early on in my scientific days, it's only half the story to do science. The other half is communicating science. We don't know how to do that. It's all for naught, right? And so I think if you're in the world of journalism, then please, there's a great way for you to get involved in this topic. I think frankly, if you're in software, you can get involved, because as we were talking about in the very beginning, if you have a home and you're thinking about how do you make this a carbon-free home, and you start to think about windows, start to think about demand response, how to think about solar and storage, and you have all these different technologies, and then you have the grid electricity coming in, you might be thinking about how do you play between these different things? How do you control them? How do you optimize for cost? Frankly, many of us are starting to look at smart thermostats. These are doing a little bit of that. So again, a great way in which you can get involved if you're a software engineer or if you're in electrical engineering. So frankly, right, I mean, my suggestion is that if you're interested in climate, and if you're also interested in storage, the easiest way to get involved is to start to look and ask yourself, what are the kinds of things that our companies are doing, academia is doing, and depending on where you're going, you're going to find a place for you to contribute towards this. And the more people that come in and contribute, I think the faster this innovation is going to be as we go to the future. So there's a certain richness here that I think we can take advantage of as you look at this closely.
Very exciting, Venkat. Thank you. I'm going to switch gears and go to the questions that we've received, and we'll try to get as many of them as time permits. The first one is really about long duration storage, and really the question, and I'll read it out. For buffering renewable energy on the grid level, it's not sufficient to buffer for a single day. You also need to buffer for seasonal changes, summer solar versus winter, use of wind, etc. And these probably require capacities of the order of terawatt hours of storage. So is that realistic with batteries? And what might be some of the solutions?
Yeah, the first thing I should say is that a battery scales very well, right? As we were talking about at the beginning, that's the beauty of these devices. So something you can make in your milliwatt hour or a watt hour in your phone can go up all the way to terawatt hour. That's one thing. But just because you can do it doesn't mean that it makes sense to do it, right? So if you kind of think about seasonal storage, one of the most important things is, what is the cost of electricity? You're not using this technology a whole lot. You hope that you put it in the ground and you use it for 100 years, but a typical technology that has chemistry does not last 100 years. So it turns out that if you do the math on this, the cost for these kinds of long duration storage has to be 10% the cost of a lithium-ion battery today. So those in the United States might have seen what is called a Earth shot. The Biden administration has come up with this concept, like the moon shot, talking about the kinds of things we have to do on Earth to solve the big challenges when it comes to climate. One of them is in long duration storage. And the target there is cut the cost of batteries or storage technology down to 10% of the lithium-ion battery cost today within the next 10 years. That's the challenge, right? 10% cost, 10% of the cost in 10 years for anything longer than 10 hours in storage duration. So the longer and longer and longer your storage becomes seasonal, as an example, you might be looking at batteries at maybe $10, $20 a kilowatt hour, as opposed to the $100+ a kilowatt hour we're talking about today. 3-4 cents a kilowatt hour sort of electricity cost, if you will, if levelized cost of electricity, as we call it. If you kind of think about instead of 13-14 cents a kilowatt hour, we have to. So significant changes that we have to think about. And so that is a huge issue. And it's not obvious that no lithium-ion battery is going to do this, right? Let's be very clear. The cost is not going to be that low just because cobalt and nickel and all the rest of the stuff is going to come. So there are batteries that can do it. I mean, there is a company, Form Energy, in the United States, that's looking at a iron-based system. Iron is kind of cheap, and they think that may be a way for them to get there. We were talking about hydrogen before, some of the form of chemical storage, that ammonia comes to mind. So these are the kinds of technology we have to look at very, very carefully. Storing some chemical in a tank somewhere and then using it little by little as you need it over many months is one way for us to think about doing this. Obviously, gasoline is a great storage media, but that produces carbon. So we have to find either a carbon-free or a carbon-neutral, at least, method of doing that. That's why hydrogen or ammonia comes to mind as a way we would do it. But certainly, as we look at these kinds of seasonal storage, it's not obvious the solution is a battery. I think that is where we have to open up our lens and sort of look at multiple technologies, including sort of chemical storage, to see if there is a way for us to get the lowest cost. Because if you don't get the cost, nobody will want to implement that particular technology. As we said, electricity is a commodity, so cost is paramount.
Thank you, Venkat. There's actually a thoughtful question that is just on those lines, and I'd like to go to that one next. What would be the impact of high demand on the supply and cost of materials? Will we only be shifting the problem as we change the demand cycles, if you will?
A fantastic question, right? I think the expectation is that after a decade of, or more than a decade of falling lithium-ion battery prices, this year will be the first year where the cost of lithium-ion battery is expected to go up. And it's supposed to go up because of the cost of cobalt and the cost of nickel, right? That's the supply chain coming in to bite us, right? So you're absolutely correct. We have to think very, very hard about whether this is going to become a dependence problem. Instead of being dependent on one primary energy, fossil fuels or something. Now you're dependent on cobalt and nickel, and you're sort of struggling with this. This could certainly happen, as we were just discussing. It seems like it's happening. This is where I'm a huge proponent of diversification. We are seeing this in the electric vehicle market with people sort of talking about different technologies that they want to start implementing. We're talking about it, as we were discussing, in grid storage, about how we have to think beyond the battery. I think this is going to be front and center going forward. I think there is going to be a role for being very careful and thinking about all the supply part, whether it's going to be through recycling, whether it's going to be through very careful sort of partnering. I think we are going to see winners and losers in the industrial side. Companies that are able to leverage and form partnerships and get the deals are going to be able to succeed. Ones that are struggling to do that are going to have problems. I remember the airline industry, maybe going back 10 plus years ago, I think Southwest had signed a long-term deal for low cost of jet fuel, and they were able to sort of push that on to consumers and really undercut everybody else, right? Those kinds of things are going to start becoming reality, and we have to think very carefully how we're going to sort of diversify. I think there's a mismatch in demand, which is sort of going up dramatically, and the fact that the supply has to come up. And now we are seeing this free for all. One of the things that we want to do, and I think every country is trying to do this, is to sort of take a step back and say, let's do this more holistically, guys. Let's just not let a free for all happen. And let's try to see if we can march in a certain way so that we can get to where we need to get to in a more systematic fashion. And I think that's going to be very important.
Super, Venkat. Thank you. There's a question here that actually, kind of talks about another key segment of the audience today, which is the information technology folks. And really, any thoughts on what might be needed from the information technology segment to make the whole system work? There's a second question, and I'll put it in there just as recognizing that they're different. But if you're talking in the world of information technology, software and software tools like AI and machine learning, are there roles for all of these in the energy system, energy storage system ecosystem, if you will? Yeah, so AI ML, like everywhere else, it's penetrating storage, right? It's everywhere. It's everywhere, from how do you discover the next big kind of chemistry using some sort of an AI or machine learning tool, to how do you manufacture better using AI and ML tools, to all the way to predicting the life of batteries using AI and ML and methods of that nature. And ultimately, it's going to come down to kind of these sort of like we were talking about before, these smart building controllers and smart home controllers that are going to have these easy ways of sort of predicting what you might be doing, like the smart thermostats that we have today. In all of these data collection and then analysis of the data, and being able to use the latest tools to predict what the data is telling us, and therefore what it means for the future, is going to be extremely important. Imagine, if you will, right, if you had climate projections, sort of real time at a local level, where you understand what's going to happen, when it's going to happen, where it's going to happen, and you combine that with the kinds of technologies you might have in your home, where you can start to play between the fact that, oh, the sun is going to be sort of shining for the next 3 hours, and then the clouds are going to start forming. I have to start sort of planning for that. I'm going to charge up the battery and wait for the cloud to come. That kind of a wonderful sort of this ecosystem of sort of technologies talking to each other is only going to happen if you can get data, learn from that,
and ultimately implement that in some sort of a smart controller. And I think we're also reaching a stage where consumers want to see stuff, that the quantified life, if you will, right? I mean, I know recently moved to an Ecobee thermostat, and I got to tell you, it's kind of fun watching the sort of the different numbers and the graphs moving around and sort of seeing how it works. Same reason why we all look at our Apple Watches and try to figure out, how much are we running and what our heart rate is and how many steps we have. So I think data is crucial to take people who are sort of smart and give them information so they can use it to their advantage to either cut the electricity price down or to reduce their emissions. And I think that's the kind of game that we have to play. Game in the sense that sort of incentivizing people to use the latest in technology, getting them excited about this, and getting them to see that as a way for them to make a better future by also sort of pressing buttons and doing something fun along the way, right? So I think there is a crucial role for people in the software industry to come into this field and do something to help us.
Excellent, Venkat. No, that I can certainly see that. I think I read an article over the weekend about how Tesla seems to have circumvented some of the challenges with the supply chain on chips by taking the chips that they have been able to get and using their software skills to change, if you will, the nature of the chips that they're using and the applications they're using them for, so to continue to maintain their supply while some of the other OEMs have struggled. So very much to the point that you just made. One more question, in kind of in the same vein, is Moore's law. We talked a little bit about kind of the loose application, but do you ever see a Moore's law type? It's recognizing it's truly not a physics law, but more of an economics kind of principle. But do you see something like that being applicable for energy density of a battery?
Yeah, the Moore's law of energy density of batteries is 5% a year, not doubling every 18 months. It's a little bit different. That is a reality, right? I mean, this is a question that often used to come up in the early days when all in Silicon Valley, people used to only know Moore's law. I used to joke with them saying, you may want to learn Faraday's law, which actually is an important thing for all electrochemists, which is a real law. But I mean, look, chemistry is hard. There's a lot of chaos in these systems. And sort of the way I think about this, right, is like Moore's law really was succeeding because, and has continued to succeed because we are kind of, we can take the same silicon wafer and start to channel them smaller and smaller, right? 10 nanometer, 5 nanometer, 3 nanometer. But there's going to be a point where we can't do that anymore, right? Quantum effects start to come in, and we have to sort of move to a new way of sort of doing these kinds of calculations. And then we have to change the material set. We can't be silicon anymore. We have to move to something else. In batteries, we've already played this game of removing all the unwanted stuff, right? So when you pack in more, you're removing extra space. That's what you're doing in a chip. And in the battery, the equivalent is, take the unwanted current collectors and make them thinner, or the unwanted separator and make that thinner. We've been playing this game for a while, to the point where if you see about a fire, the fires happen because somebody made it too thin, the separator or something like that, and shorts the battery. So we've kind of hit those, maybe not quite hit the limits, but are getting to the point where we're hitting those limits, right? So batteries evolve because we are trying to, from an energy density perspective, because we are trying to change the chemistry. So that's the tough part. So we are not at a place where it's engineering advances. We are at a stage where it's chemistry advances. And that's why it's 5% energy density year. Cost is different, right? Because there we took advantage of mass manufacturing and the sort of the engineering, if you will, to kind of cut the cost down. But even there, as we were talking before, we might be at a floor where chemistry changes are what is going to really help us as we go to the future. So unfortunately, expecting a doubling every 18 months of anything in batteries is just not realistic at this moment. So.
Thank you, Venkat. I recognize we're almost out of time, so maybe one quick question as the final one. We've talked about a number of the participants and stakeholders in the innovation ecosystem, but one that we have only skirted is the role of government. And I don't know if you have a quick answer that you could provide, on the role of government, and then we'll wrap up at that.
Yeah, very briefly, extremely important, as you know. I think everybody, academics, all the way to industry, wants a steady hand. They want to know what the future holds. So having policies that can stand the test of time, can last a decade or so, and clear signals that one is moving towards a new way of using energy, that we're going to be in a different energy economy in the coming century or this century compared to the one before, is going to be extremely important. And only one set can do that. Those are governments all over the world. COP26 was, I guess, one of many starts that we've had, but really it comes down to the world governments coming together and setting the tone so the rest of us can follow the lead and know there is going to be long-term sustainability for the technology that we're pursuing.
Thank you, Venkat. That was right on point. I recognize we're just about out of time. So let me first start by thanking you for the very rich discussion. I mean, I thought that you highlighted very well the challenges, the opportunities, the trends, the applications in this space. Very exciting and very important, I think, in every aspect of our life over the coming decades. So thank you for sharing your insights and knowledge in this space. I'd like to also thank all of those who are participating today and listening to this discussion. I hope you found it informative. And last but certainly not least, I'd like to thank the team from Nagarro for making this kind of a discussion possible. We appreciate your interest and we appreciate what you're doing with the Sommelier Series. Thank you, everyone. With that, have a great day.
Thank you so much.